Good day, ladies and gentlemen, and have a warm welcome here from Pretoria. This is Sarel van Grenen, aka Mr. VG, and today we are going to do a lovely question from an IEB paper that's going to force you to think a bit differently about how you approach geometry. Now, this kind of question is one that's actually going to require some construction to finish it off. For those of you that are watching and are from an IEB, a non-government school, a private school, look out for something like this in your exam. For the rest of you, I encourage you, do not just go, oh, this is a private school thing, I'm not going to watch this. Please, your teacher may ask it in this prelim. You never ever know. So I encourage you, focus, be there 100%, and also just have a bit of fun. So let's dive into this specific question. This specific question asked us the following. In the diagram below, a circle is drawn passing through B, C, D, and also A. Angle BED is theta, and BE and ED are tangents at B and D respectively. Okay, let's quickly stop. What does that mean on the sketch? First of all, it means theorem 7. No, it doesn't, because there's no center of a circle. It does go towards theorem 8, which says BE is the same as ED. I don't have anything else. Oh no, wait, I actually do. What about cyclic quads? Because ABCD is actually a cyclic quad. Let's not forget about that. And that's actually going to help me, because in the question, it asks me to calculate angle C. So if I can get angle A, then I can get angle C. I hope that you guys are getting my drift when I'm talking about A and then C, because together they add up to 180 degrees. So let's quickly have a look now at the scenario. I am sitting with a tough one here, because I don't have any more information. How am I going to relate angle C to angle E where theta is? Now, please don't freak out like I was freaking out there. What if I can construct BD? Because if I've got BD, then I actually have an isosceles triangle. And also, I can apply theorem 9, which is the tan-chord theorem, that both that B, so angle EBD, as well as angle EDB, are equal to angle A because of tan-chord theorem. I so badly wish I could show you the finger method with this. If you haven't seen the finger method, go and look at the previous videos where I discuss how to do geometry. How do I approach Euclidean geometry? On those videos, I show you the finger method if you're still struggling with theorem 9. So let's quickly have a look. If I can get B or D in terms of theta, then I can get A, and then I can get C. So that's going to be my approach. Interesting, look at the way I did that. I said for me to get C, I want to get A. But for me to get A, I need to get either that red B or the red D, and then relate that to E. So let's try and do that. So first of all, I'm going to tell the examiner, construct BD. I have to tell them what I do because it hasn't been given on the sketch. Next up, I'm going to say, well, BE is equal to DE because they are tangents from the same point. After I've done this, I can now start going, okay, you know what? Why is the red B's the same? Well, angle DBE is equal to angle BED because they are angles opposite equal sides. And therefore, I can say that those two angles, the sum of them and theta is equal to 180 degrees because of interior angles of a triangle. By looking at this now, I can get that angle BDE is equal to 180 degrees minus theta divided by 2. That follows directly from there, because remember, BDE is the same as DBE. If you are unsure about how I got to that, please try it yourself or ask a teacher. You could even email me and go, "Sir, I don't know." And I will gladly help you with how I got to that. Now next up, I'm just going to divide each of the 180 degrees and the theta by 2, which leaves me with 90 degrees minus theta over 2. Please, just in your mind, hit the pause button and look at where you want to go. I'm seeing a theta over 2, which means I'm going, this is nice. I'm getting closer to where I want to go. Now next up, I'm going to move over to red. So angle BDE is equal to angle A because of theorem 9, the tan chord. So angle A is actually equal to, let me go to my red, angle A is actually equal to 90 degrees minus theta over 2. Again, remember, if I have angle A, I can get angle BCD. Why? Because together they add up to 180 degrees because of opposite angles of a cyclic quad. Now, if I substitute that expression for A into that equation, I'm sitting with this. If I'm now solving for angle BCD, I'm just going to take that 90 minus theta over 2 across, and it's going to be plus theta over 2, Mr. VG. Let's not make those mistakes. And therefore, I'm going to sit with 180 degrees minus 90, which is 90, and therefore 90 degrees plus theta over 2, which is exactly where I want to go. Booyah! Fantastic. I love this. We've done it. I know. When you look at something like this, it's easy to freak out. Especially if you are, if you're struggling with Euclidean geometry. I encourage you to think a bit, especially when you are unsure of this. What could I draw in to make the sum easier? If you are from a GDE school, a public school, please, drawing in, I doubt whether you'll get a question like this. But if you do, it's your last option. IEB school, IEB scholars, look out for one question like this in your exam. And don't forget, you have the option of drawing in a missing side to make your life easier. What a beautiful sum. I hope that you are coming all right with Euclidean geometry. If not, do not give up. This is Mr. VG signing out. Have a beautiful, wonderful, fantastic rest of your day. And remember, you are awesome. Keep well. Cheers.